No, no, no,
VCC
no,
or VDD always.
no, no. It's not. See, for example, if there is an AND gate and the output has a stuck at one fault, it doesn't mean that the output is connected to one. Okay, it could be because one of the inputs has a problem. Okay, if the input is maybe connected to ground, right? Or if one of
Mm.
the PMOS transistors is permanently on, so there may be many reasons why it behaves as though it is a stuck at one. Okay, it doesn't mean that it is connected to one.
Okay.
Okay, yeah,
So the fault may come from a device level also due to
yeah, yeah. Device
defects
level
in the.
only. See, ultimately the circuit consists of devices only, right? So the gates, etc., are a one abstraction, right? So the faults occur either because of open circuits or short circuits or maybe some transistor is permanently on or permanently off because of mask misalignment, right? Maybe the channel has not even been formed. So there may be so many reasons why uh, you know there is a malfunction in the circuit, and so those are defects. Okay, the same one defect may manifest itself as a number of different faults. So we only talk about faults because it's easier to talk about faults. If we could do, we would love to talk about defects and try to directly look at defects, but it turns out it's very hard to look at defects, right? It's already hard to talk about the faults. So going to the level of physical defects and trying to figure out whether a particular physical defect is there or not is very difficult. So people don't worry about defects. You understand, no?
Yeah, yes, sir.
Yeah,
And sir, what
yeah.
are the chances for a node to be in a floating stage, not neither one nor zero? Will it occur?
Yeah, it can occur. See, for example, um, see if there is a that is why we sometimes write it as an unknown, right? See, when you cannot tell whether the output is a zero or a one, we sort of assume that it is an unknown value. So, see, even an inverter, okay. See, when you apply zero, see, remember zero means logic zero means it is some voltage level only, right? It's it's a
Yes.
value in the range zero to that VIL, right? There is up to
Mm,
some
correct.
value of the voltage we consider it as a low. So now, if you apply a low voltage, the output will be close to VDD. It will be a high voltage. Similarly, the other way around, right? If you apply a logic 1, you will get a logic 0. Now the question is, what happens if you apply a voltage which is neither 0 nor 1, somewhere in between, right? Then in principle, the inverter will give, you may have seen, no, in that inverter characteristics, if you are able to apply VDD by 2 or something like that, output will be VDD by 2. Okay,
Mm, yes.
but it is not a stable state. Okay, very quickly it will go to either 0 or 1, depending on the noise that may be there, right? Remember that we will never be able to hold the value at VDD by 2 in a stable way, because there will be always some noise or something like that in the circuit. Okay, so
Yes,
in
sir.
principle it is possible.
Yes.
Yeah.
Mm. And sir, the things we are learning, so how are they actually being implemented in the big companies and all? So do they have a software in which they check
Yes.
all this?
You mean test generation and all that? Yeah, there are software tools available for generating the fault model, TTPG, right? See, for example, Synopsys, right? They have a tool called Tetramax. Now they, I think, call it TestMax. Then Cadence has a tool suite called as Modus, and then Descent, or what used to be called Mentor Graphics. So these are the three big companies which have a lot of tools related to test. So yeah, I mean, you need tools.
So there won't be any special hardware for doing this. Everything will be software,
I
is it?
think if you wait for a little longer in the course, we talk about design for test. So I don't know whether
Ah,
we have come to that scan test and all those things, but later you will see that in the course we'll talk about some special hardware that we have to insert in order to make testing more easier. So we have this scan testing, we have logic based, memory based. So yeah, a lot of hardware gets inserted into the circuit in order to allow, you know, uh, testing to be feasible. Otherwise, you can't do. If you don't insert any hardware and you try to do testing without special hardware in the circuit, it is too difficult to do. Yeah.
yes. So this is similar to the last lecture of week 4 where we insert a gate or where the
That is testability.
controller
Yeah,
will
you are
be.
talking about how to improve testability, right? Yeah, that's also
That's
one way.
the,
Yeah, in the same way, see, I don't know whether we have already started covering sequential testing in the lectures. So, sequential testing, when we cover, you will realize that it is very difficult to generate test vectors for sequential circuits unless you are willing to modify that circuit in some way. Okay, so that is what sequential testing or scan testing is all about, right? So, you just wait a little, that part will be covered.
yes. Answer in bridge fault. Why do
Yeah.
we model it into some into AND gate and some other into OR gate?
No, no, it's not that some are modeled as AND or some are see, both are different models, AND bridge and OR bridge. So when generating bridge fault model, unfortunately, you have to do both. You understand, no? So you have to
Yes.
assume that for AND bridge, you have to generate a test. For OR bridge, also, you have to generate a test. Sometimes you may not have a test for OR bridge, and sometimes you may not have a test for AND bridge. Okay, but
Mm.
you will have to consider both of them.
Okay.
Yeah, yeah,
So sir, the bridge fault is when two very closely going lines are shorted and
yeah. Mhm.
the values it possesses are differing with each other. Is it? I
Yes.
mean, one line has 1, another has 0, and when they are shorted,
Only
what
then
happens? Is it?
the see bridge fault will be visible if the values are different. See, if the values are same, then the fault got
Correct.
masked.
Yes, yes.
If you have a stuck at zero fault and the test also places a zero, right? Then it really, you're not exposing the fault. Okay. In the same way, if you have a bridge fault and you are placing both the lines at zero or both the lines at one, you have not exposed that fault. So to activate a bridge
Mm.
fault, you have to place opposite values.
Yes.
Okay. Anything else?
So sir,
Sir,
the
about
Yeah, go ahead. Go ahead.
Muthu, you asked me about.
uh, maybe I'll ask later, ma'am, after you.
Sir, actually, I just wanted to ask, like, is there a convention that if we propagate one backwards, then we have to propagate D forward, and if we propagate zero backward, then we have to propagate D bar forward, or we can do it either ways?
No, no. See, understand the point. No, see, if there is a wire on which we have to test for stuck at zero fault, then we have to activate the fault by putting a one on that wire.
Yes. So
So
if we
that
activate one, then is it a convention to propagate D forward, or we can propagate either D or D bar
no,
forward?
no, it when you place a 1 on a wire which has a stuck at 0 fault, that 1/0 is called D.
Okay.
That 1/0 is called a D. What do you mean by propagate a D or D bar? See, when I propagate, ultimately what I get at the output may be a D or a D bar. You understand,
Yes,
no?
yes, yes.
So it doesn't make sense to say propagate a D or propagate a D bar. We have to send the D such that either a D or a D bar appears on one of the outputs.
Okay, okay, okay. Got it, sir.
Okay. All right.
Sir,
Hmm.
like D algorithm and PODEM,
Hmm.
do we have anything more or more efficient or more?
Uh, After D algorithm and PODEM algorithm came, uh, people may have developed more, bells and whistles to the same thing, right? See, as these algorithms were very old. I think they were invented, I think, in the 70s, I think, right? So they have been around for a long time. So today, as so many years have passed, I think PODEM may have come in the 80s. D algorithm, I think, in the 70s. So PODEM itself was a improvement on D algorithm, right? In the same way, people would have added a number of bells and whistles to make it even more efficient and so on. But I don't believe there is anything significantly different. You understand, no? See, ultimately, it is
Mm.
a that instead of basically it's backtracking. If you can improve the efficiency of backtracking by using a lot of different heuristics, right? Then you can keep on improving the efficiency of the algorithm. So these real ATPG tools, they may use heuristics to reduce the number of backtracks.
Yes, sir.
Yeah.
And sir, the convention, the way we give a notation for controllability and observability, we
Hmm.
see the scope, right?
Hmm.
So is it a standard or widely used convention?
That
Or,
CC and all that
mm,
I have talked about in the class. No?
uh,
Yeah, that is standard. That is standard.
okay.
Yeah. Combinational controllability, combinational observability, CC, CO.
Yes, sir. And adding one if we go one level deeper.
Sir, you're not audible. Muthu,
Yes, ma'am.
can you please share this Gmeet link in the G space?
Yeah, sure, ma'am.
Okay, thank you.
Yeah. Sorry for that disruption. What was the question you were asking? Hello.
Yeah, sir.
Yeah. What was the question?
I think I was asking the scope. Is it
That is,
universal?
yeah. I mean, scope is one way to measure controllability, observability. I think signal probability is also another thing that people have used. So yeah, I think there will be many other ways to measure controllability, observability. Scope is one of them. Yeah.
Sure, sir.
Yeah.
Good evening, sir.
Yeah. Good evening. Good evening. More questions?
So nothing at the moment. I mean, I went through week 4, and I think that was the most interesting one so far,
Hmm.
because I think all of the concepts have been laid. So we have a fair
Hmm.
idea of what we want to, of what we can expect. And so it was like very easy,
Hmm.
like a breeze. There were two topics that you mentioned,
Hmm.
the T algorithm and the PODEC algorithm.
Hmm.
So
Yes.
yeah, I mean, that was very easy. Yeah. It's just quiz one. The only I would not say drawback, but the only concern is, since we do not have any previous batch, so we don't know what to expect with respect to quiz. But
Hmm.
if possible, if we can get like a
It will be
mock
based on
for
your.
quiz, that will be
It will be very similar to you have been doing all these practice questions and all that. So you can expect something similar only. It will expect we. I expect you to be able to apply the concepts that you learned in the class, right? It's a paper and pencil exam,
correct.
so you will be asked to write. Yeah, yeah.
Right, sir.
You don't have to be worried so much about the exam. It will be if you have understood the concepts, I don't think you will have any problem in doing it.
Sure, sure.
Sir.
Yeah.
So nowadays all the gates are being made using CMOS. Is it?
Yes. Yes. CMOS is the technology. Yes. Yes.
And the transistor, is it MOSFET or FinFET? Or
If you go, see, the thing is, FinFETs, etc., make sense when you have very, technologies like less than 10 nanometer, etc. Okay, 20 nanometer, 10 nanometer, 5. That is when you have to worry about different kinds of transistors. But not everybody uses such technologies. Okay, so quite a lot of industry is still using 65 nanometer, 45 nanometer. Um, so only in some extreme cases, see if you are a AMD or a Intel or an IBM, you may need those technologies like 10 nanometer, 5 nanometer, etc. Okay, but for most applications, you don't need such technologies. So it will be the conventional MOS, CMOS.
yes, sir.
Yeah. FinFETs are being used, but like I said, in companies like I told you, right? I mean, AMD or Intel, IBM, not again in all the applications. Okay, they will also have multiple, fab lines, and they will also be using conventional, the older technologies are still being used.
Okay, sir.
Sir, a follow-up on the question asked by Muthu about scope method. So in control systems, we have that concept of state model, and then we use Kalman's test to find controllability and observability.
Hmm, 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 hmm.
So that is another method, right?
I think in controls, see, these are digital circuits that we are talking about. So whether they
Okay.
directly relate to digital circuits, I'm not sure. Huh? These control systems generally they are not digital control, right? I mean, I may be wrong, but
Yeah, I mean, we do use Laplace transform and other things. So
huh,
yes.
huh. So I think if you have an analog circuit, maybe those concepts can be applied, but
Okay. And
not
not for
in digital. I don't think so.
okay, sir.
Yeah. Here we are worried whether we can activate the fault, right? If the one controllability of a wire is very poor, then activating stuck at zero fault on that line will be very difficult. So we'll have to think of some way to improve the one controllability. So in a control theory setup, um, I suppose similar idea maybe there. I mean, maybe it's possible to improve the controllability and all that. But I think these are digital circuits, so they may not directly apply. Analog circuits, you may be able to relate. Okay, so it's a good question. You can think about. You can take some analog circuit and see whether the same ideas can be applied. Okay, it's a good question. Yeah. So you have taken a course on control theory last semester or something?
No, sir, I'm an instructor. Actually, I studied control systems during gate preparation.
Oh, I thought you were one of the. Okay, okay, fine, sure. So how many students are actually in this class? 7 or 8, is it?
Sir, I'm not aware of that.
Yeah, I don't think there are many students.
15, around 12 or 13.
Oh, I see. Okay. You are from Madras? Where are you from?
No, sir, I'm not from Madras, but I'm in Tamil Nadu.
Okay. What about the other guy? Namaya? Namaya or Namal?
Sir, no, yes, sir. Sir, no, sir.
Ah,
I am also not from Madras, sir. I'm from Delhi.
Delhi. Okay. Subhash is, I think, located right now in Madras. Subhash, I think, he has some TA or something like that, and he is still in IIT Madras. And I met
Yeah,
there is one girl student also. I think I met her, and one more student I met when I went.
Sir, when did you meet them exactly?
When I went last time, I think sometime in July. I think, no, wait, not July. September. I think I went. At that time I went. Your classes had just were about to start.
Oh, I see.
Is
Okay.
it August?
I think
Huh?
Vaibhavi, I think you are mentioning.
Huh?
Vaibhavi.
When did your classes start? Tell me again.
September
What was
ending.
it? Huh?
For this one, it
September
ended.
ending.
So I think they had all just come. So I met the instructors and I met only two students I met from your class. There was no class. They just happened to be there and I met.
Yes, sir. They are both TAs and also studying
I think so. Yeah.
offline class.
Three students, two or three students I met. Okay. So
Okay.
if you don't have any questions, we can maybe close it. Yeah.
Sir, the pin muxing,
Ah,
pin multiplexing. So, how is it done exactly?
pin multiplexing means when
So,
you don't
is
want
it,
to have so many output pins or input pins, you will have to multiplex, right? See, at any time, suppose only one of the pins is observed, right? Then you'll have to introduce a mux and allow only one of them to be observed through the mux. Okay, it's a straightforward concept. So let us say there are four pins. I want to share one output pin across four. So I will, give them through a multiplexer and selectively, observe one of them at a time. Okay, in the same way, input also, right? So I don't have enough input pins, so I will, sort of use a demultiplexing concept.
yes, sir. So, this will be helpful only when so many output lines are to be multiplexed, right? If, let's say, if we have two and want to observe one, it won't be that quite
See, the
useful.
pin matching is used when, see, the more pins you have, the more expensive the circuit, right? The package becomes more and more expensive.
Hmm.
So when you can't afford a higher cost package, people try to see whether they can use pin multiplexing. Understood, no?
Yeah, yes, sir.
Yeah. Okay.
So are there any other questions?
Okay. So maybe we can close.
Yes, sir. Thank you.
Okay. Thank you, guys. Thank you. All the best for your exam.
Thank you, sir. And thank you, ma'am.